Hello, everyone. Welcome to Hey Classroom about electrical circuit fundamentals. Today we are going to talk about the nature of electricity as the opening lecture of this course. First, let's take a trip back in time to see how humanity first stumbled onto electricity. Picture this. The ancient Greeks are rubbing a piece of amber, yes, that shiny golden resin, with some wool. And then they notice something curious. When they bring the amber to a light with things like feathers here, the feather get absorbed by the amber. So what's going on here? When you rub the amber against the wool, the friction gets those tiny electrons moving. They jump from the amber to the wool. That leaves the amber with positive charges. As we bring the charged amber near a feather, and whoosh, the feather gets pulled in by this invisible electrostatic force. Pretty cool, right? And here is a fun fact. The word electricity actually comes from this discovery. Why? Because in Greek, amber is called electron. So in such a way, electricity all started with a little rubbing and a lot of curiosity. Similarly, it is found that glass wrapped with silk and ebonite wrapped with fur do the same thing. Here is where it gets interesting. When we bring a silk wrapped glass rod to a fur wrapped ebonite rod, they attract each other. But how about two glass rods? They repel each other. Same with two ebonite rods. This leads to a key discovery. There are two types of electricity, positive and negative. Like charges will repel each other, and unlike charges will attract each other. Therefore, a fundamental law was born. Here's another demonstration. Imagine we have a light bulb hanging from a thread. We'll charge it up. And here's what happens. If we bring another ball with the same charge nearby, they push each other away. But if we swap it for a ball with the opposite charge, they will pull together each other. Same charges repel, opposites attract. It's a simple rule that shows how electricity behaves. Alright, now let's dig down how electrification by friction really works. It's all about what's going on inside the atoms. Take the atom like a tiny solar system. At the center, we've got a nucleus. Surrounding it, electrons, circulating around like little orbiting planets. The nucleus is packed with protons and neutrons. Now here's the key. Electrons carry a negative charge, while protons in the nucleus are positive. Neutrons, they are just along for the ride, no charge at all. Inside each atom, we've got protons in the nucleus and electrons orbiting around. Here's the deal. There's usually the same number of protons and electrons. They cancel each other perfectly, so normally an atom is just electrically neutral. No positive, no negative, just neutral. So when we rub two things together, just like the amber and the wool we talked about earlier, the friction makes some of those electrons jump from one material to the other. That leaves one side positive and the other side negative. Why do the electrons stick around the nucleus in first place? It's an electric pull. The positive nucleus keeps those negative electrons in orbit by electrostatic force, kind of like gravity holding satellites around our planet. Now, let's zoom in on those electrons circulating around the nucleus. Here's the cool part. They don't just orbit anywhere they like. Nope, they are very picky. Electrons can only hang out in specific rings or shells and fixed distance from the nucleus, kind of like lanes on a racetrack. And each shell, It's got a limit on how many electrons it can hold. No overcrowding allowed. The outermost shell is the VIP section. We call it the valence shell. The electrons in it are the valence electrons. These guys are the real ones who decide how an atom behaves electrically. So when we talk about electricity, it's usually about these outer shell electrons. As we mentioned before, an atom is just electrically neutral because it has the same number of protons and electrons. But what happens if things get shaken up? If an atom loses an electron, okay, there goes some negative charges. It tips the scales and becomes a positive ions. On the other side, if it snags an extra electron, it picks up more negative charges and turns into a negative ion. It's all about that keep of the balance or the break of the balance. This triggers electrical actions. Alright, let's see what happens when charged objects get up close. Imagine we have two rods, just like we introduced before. One is silk-wrapped glass with positive charges, and the other one is fur-wrapped ebonite with negative charges. The ebonite rod is packed with extra electrons, and the glass rod is short of electrons. When they are connected by a metallic wire, the electrons will rush from the negative side, where they are overflowing, to the positive side, where they are desperately needed. It's like water flowing from a full bucket to an empty one. Even if one of the rods is neutral or just less negative, those electrons will still make this kind of flow. This movement of electrons is called electric current. Now, if we swap that metal for something else like rubber, all the electrons will stop. That's where we get conductors and insulators. Conductors, like metals, are the electron superhighway, letting current flow easy peasy. Insulators, they are the road blockers, saying no way to electron traffic. Okay, let's talk about what gets electrons moving between these two charged rods. Here, the positively charged rod is loaded with a plus sign, and the negatively charged rod is sticking with a minus sign. We call the positive one has a positive potential, and the negative one has a negative potential. We call that difference between them a potential difference. When they are opposites like this, they've got this potential difference to trigger a flow of electrons between them. Now think the potential difference as electrical pressure to make something happen. Give it a path, like a metallic wire that conducts. The pressure turns into an electric current flowing from one side to the other. It's like a flipping a switch and letting the energy loose. Here's a twist. Even two bodies with the same charge, like two negative ones, can have a potential difference if one is charged up more than the other ones. Alright, let's zoom into what happens inside a conductor with electricity getting going. Take an electric lamp for example. Inside, there is a super thin tungsten wire, we call it filament. It is sealed in a glass bulb with no air. Imagine if we apply a potential difference. Think of connecting it with a battery. This makes one end negative and the other end positive. An electron in there feels the push. It's repelled from the negative side and pulled toward the positive side. But it's not a straight shot. The atoms in the conductor are like a crowd in the way, slowing it down. So this electron doesn't zoom across. It bounces around, zigzagging from atom to atoms, just drifting toward the positive end. Every time it bumps into atoms, it loses a little energy as heat. Now multiply that by tons of electrons flowing together. These electron-atom collisions can go wild, and the heat can really add up until the filament glows white. Okay, let's talk about how we draw electricity in actions. You can draw the same setup in tons of ways. Here's a super simple setup: a battery, a switch, and a lamp. Here on the left side, it is a visual picture. This type of drawing could easily click for most of us. It's just easier to get. However, the more parts you add, the crazier the drawing can be. Things can start looking like a puzzle. So if you are jumping into a project like building a circuit or design a PCB board, using the graphic symbol is a must. Look at the circuit diagram on the right side. It is a much simpler sketch where electronic symbols are used for the parts and the lines shows the wire connecting them. As a result, circuit diagram using graphic electronic symbols is used in electric circuit design. Now, let's dig down a little bit more. In the battery symbol, the long bar is the positive end and the short one is the negative end. When you flip that switch closed, the electrons move from the negative side through the lamp, lighting it up, and then head back to the positive side. Here are the most used electronic component symbols used in circuit diagram, such as diode, resistors, capacitors, lamp, transformers. Hopefully you could enjoy in the sea of electronic symbols. Okay, that's all for today. See you next class.